In this session, I will explain theorems on normal subgroups. So, first theorem, if capital M comma N are two normal subgroups of Z, normal subgroups of Z such that M intersection N equal to singleton E, then every element of M commutes with every element of N. Every element of M commutes with every element of N. Every element of N. So, this is the statement. M comma N are two normal subgroup of Z such that M intersection N equal to singleton E. So, we have to prove that. That means we have to prove that every element of M commutes with every element of N. So, already you know that every element of M commutes with every element of N means, so Mn equal to Nm. So, we have to prove first of all Mn equal to Nm. So, first of all, given proof M comma N are two normal subgroup of Z. Let M comma N are two normal subgroups of Z, and given that M intersection N equal to singleton E, and given that condition M intersection N equal to singleton E. So, we have to prove that every element of M commutes with every element of N. We have to prove that every element of M commutes with every element of N. That means Mn equal to Nm or Nm equal to Mn. So, first of all, let small n belongs to capital N. Small n belongs to capital N. So, N inverse also belongs to N. So, N is a normal subgroup of Z. So, that means N belongs to N. It can be written as N inverse belongs to N. Already you know that N is a normal. So, N is a normal subgroup of Z. So, already you know that N belongs to N, N inverse belongs to N. First of all, M belongs to M, N belongs to N. First of all, small n belongs to capital N and small m belongs to capital M. Since n belongs to N, since small n belongs to capital N, so that means N inverse belongs to capital N. Since N is normal, since N is normal in Z, since N is normal in Z and M belongs to M and M belongs to M, already you know that N is a normal subgroup of Z. Definition is X inverse belongs to H. So, H is a subgroup of Z. H is a normal subgroup of Z. So, by using definition of normal subgroup, already you know that N is a normal in Z. So, M belongs to M, N belongs to N, N inverse belongs to N. So, you can write M N inverse, M inverse belongs to N. So N is normal. N is normal in Z. So, you can write N belongs to N. So, N inverse also exists. N inverse belongs to N. So, N is a normal in Z and M belongs to M. So, can be written as M into N inverse into M inverse belongs to n. So similarly x inverse belongs to H. So H belongs to Z, H inverse also belongs to Z. Can be written as x inverse x inverse belongs to Z. So M inverse belongs to N. So by closure law, by closure in N, by closure in n belongs to n, by closure in n, that means, so already you know that by closure law property a comma b belongs to Z. So it can be written as with respect to multiplication a dot b belongs to Z. So by using this property, so n belongs to n, n inverse belongs to n. So by closure law, n belongs to n, n inverse belongs to n. By closure law, n inverse belongs to n. So since M is normal, already you know that M comma n are two normal subgroup of Z. So since n is normal, so n inverse belongs to n. Since M is normal, so already you know that M is normal, so it can be written as n inverse belongs to M. M is normal, so n inverse belongs to M. So n inverse belongs to M, so M inverse belongs to M. So M is normal, small m belongs to capital M. So it can be and also can be written as M inverse belongs to M. This property also exists. So M inverse belongs to N. So by closure law, or by closure in M, so already you know that n inverse belongs to M, M inverse belongs to M. So that means already you know that a comma b belongs to Z with respect to multiplication a b belongs to Z. So it can be written as n inverse belongs to M, M inverse belongs to M. So it can be written as n inverse M inverse belongs to M. So with respect to multiplication n inverse, so a into b, so n inverse M inverse belongs to M. So we observe that n inverse M inverse belongs to N, n inverse M inverse belongs to M. For example 1, 2. So we observe that from 1 and 2, so common elements n and M is n inverse M inverse. So n comma M are common element is n inverse M inverse. So it can be written as, already you know that, for example, small a belongs to N, small a belongs to H. So common element N and H is A. So it can be written as A belongs to H intersection A. So common element can be written as H intersection N. So it can be written as from 1 and 2, n inverse M inverse belongs to M intersection N. So common element is n inverse M inverse. So but already given that M intersection N equal to singleton E. So but M intersection N equal to singleton E. So singleton E, so it can be written as M intersection N value is M intersection N can be written as N inverse and M inverse. So n inverse M inverse equal to E. So multiply on both side E, n inverse M inverse, multiply on both sides M into M is the identity element. So changing the brackets M and n inverse M inverse into M equal to EM. So E is the identity element. So value is M. So next M inverse into M, already you know that A inverse into A value is A inverse into A value is E. So n inverse m inverse into m is E equal to m. So n inverse equal to m. So multiply on both sides n. So n inverse into n into m into n. So n inverse into n value is E. So n m E into equal to m into n. Already you know that E is the identity element, so it can be written as so n m equal to m n. So that means every element of m commutes with every element of n. So therefore every element of m commutes with every element of n. So next theorem, if n is a normal subgroup of Z, H is a subgroup of Z, we have to prove that Hn is a subgroup of Z. Proof. Already given that n is a normal subgroup of Z, H is a subgroup of Z. So we have to prove that Hn is a subgroup of Z. So first given n is a normal subgroup of Z, and H be a subgroup of Z, we have to prove that statement n is a normal subgroup of Z, H is a subgroup of Z. So prove that Hn is a subgroup of Z. So already given that n is a normal subgroup of Z, H is a subgroup of Z. So we have to prove that Hn is a subgroup of Z. Already you know that a normal subgroup of Z is commutative with every complex of H in Z, complex or subset. So already you know that by noun theorem, every element of a normal subgroup of Z is commutative with every complex of H in Z, with every complex or subset, with every subset of H in Z. So by using this theorem, so it can be written as H is a subgroup subset of n. So that means, so it can be written as Hn equal to NH. So already you know that by noun theorem the necessary and sufficient condition H comma K are subgroup of Z, then HK is a subgroup of Z if and only if HK equal to KH. So by noun theorem, so statement is the necessary and sufficient condition H comma K are subgroup of Z, then HK is a subgroup of Z. So if and only if HK equal to KH. So by using this theorem, so already you know that Hn equal to NH. So by using this theorem, if and only if HK equal to KH, so HK is a subgroup of Z. So Hn equal to NH, so Hn is a subgroup of Z. So by using theorem, by noun theorem, so H comma K, so given theorem H comma N are subgroups of Z and Hn equal to NH. So that implies, so Hn equal to NH. So HK equal to KH, HK is a subgroup of Z. So if and only if means let HK is a subgroup of Z, then HK equal to KH. So second part, conversely, HK equal to KH, then HK is a subgroup of Z. So Hn equal to NH, so Hn is a subgroup of Z. Is a subgroup of Z. So first of all, given n is a normal subgroup of Z, H is be a subgroup of Z. So we have to prove that Hn is a subgroup of Z. So we know that, already know that a normal subgroup of Z is commutative with every complex of H in Z. So that means Hn equal to NH. So H comma N are subgroup of Z. So can be written as Hn equal to NH. So Hn equal to NH. That means Hn is a subgroup of Z. So by using this theorem. So next definition, normalizer of A in Z. So next theorem, so next definition, normalizer. Already you know that normalizer definition. So first of all, let definition, if Z is a group, if Z is a group and A belongs to Z, small a belongs to capital Z, then set of X belongs to Z such that XA equal to AX. So every element commutes with, so every element commutes, so XA equal to AX. So X belongs to Z is called normalizer of A in Z. Of A in Z. So this is the definition. Already you know the definition. So theorem, if G is a group and A belongs to Z, then X belongs to G such that AXA equal to AX is called normalizer of A in Z. So by using this definition, so solve the theorem. So theorem statement is, so if Z is a group and A belongs to Z, then normalizer of A in Z is a subgroup of Z. Normalizer of A in Z is a subgroup of Z. So proof. First, given Z is a group and A belongs to Z. So let Z is a group and A belongs to Z. So consider n of A equal to, already you know that n of A equal to x belongs to Z such that xa equal to Ax. So already you know that. Consider n of A equal to set of x belongs to Z such that xa equal to Ax. So we have to prove that normalizer n of A is a subgroup of Z. So we have to prove that n of A is a subgroup of Z. We have to prove that n of A is a subgroup of Z. So already you know that subgroup definition. So first of all we have to prove, or we have to show that n of A is non-empty. So let, since already you know that A belongs to Z, so since A belongs to Z, so A belongs to Z, so existence of identity property is A into E equal to E into A equal to A. So A into E value is A, E into A value is A. So AE equal to EA. So that means AE equal to EA. So every same definition, XA equal to AX. So AE equal to EA. So that means non-empty. So non-empty subset. So A belongs to Z. Already given that A belongs to Z. Since already you know that E belongs to Z. A belongs to Z, E belongs to Z. It can be written as AE equal to EA equal to A. So that means can be written as, only consider AE equal to EA. So only consider AE equal to EA. So AE equal to EA is normalizer. So therefore E belongs to n of A. A belongs to Z. So E belongs to n of A. So E belongs to n of A means, so n of A is non-empty subset of Z. So A belongs to Z. So it can be written as A equal to E equal to A. So A equal to EA. So E also belongs to n of A. So E belong, already you know that since A belongs to Z, E belongs to Z. Since E belongs to Z, A belongs to Z. So by using existence of identity A equal to E equal to A. So that means A equal to EA. So E belongs to n of A. A belongs to n of A. So E belongs to n of A. N of A is a non-empty subset of Z. So next we have to prove, so subgroup already you know that by noun theorem. So AB belongs to H, the necessary and sufficient condition. So the necessary and sufficient condition. So H is a subgroup of Z. H is a subgroup of Z. So AB belongs to H. A inverse H is a subgroup of Z if and only if AB belongs to H. So second property, A inverse belongs to H. So H is a subgroup of Z. So we have to, this theorem we have to prove, already you know that n of A is a non-empty subset of Z. So we have to prove. So consider n elements. So already XA equal to AX. So consider x1 comma x2 belongs to n of A. N of A is a normalizer. Normalizer, we have to prove normalizer is a subgroup of Z. So x1 comma x2 belongs to n of A. So by using, we have to prove x1, x2 belongs to n of A. So this is first one. So second one, x1 inverse belongs to n of A. So we have to prove x1 into, with respect to multiplication, x1 into x2 belongs to n of a. So second one, x1 inverse belongs to n of a. So proof x1 comma x2 belongs to n of a. So we have to prove x1 into x2 belongs to n of a. So let x1 belongs to x2 belongs to, so x1 comma x2 belongs to n of a. So it can be written as, already you know that x belongs to z, so xa equal to ax. So x1 comma x2 belongs to n of a, so it can be written as, so ax1 equal to x1a and ax2 equal to x2a. So first we have to prove x1 into x2 belongs to n of a. So let us consider a into x1 into x2. So a into x1 into x2, so changing the brackets, so ax1 into x2. So ax1 can be written as, x1a, so x1a into x2. So it can be written as, so changing the brackets, so x1 into ax2. So ax2 can be written as, x2a, so x1 into x2a. So changing the brackets, x1 into x2 into a. So consider a into x1 into x2. So finally x1 into x2 a. So therefore a into x1 x2 equal to x1 x2 into a. So that means ax equal to xa, a means n of a belongs to n of a. So x1 x2 belongs to, therefore x1 x2 belongs to n of a. So that means x1 x2 belongs to n of a. So first part. So second part is, let's consider x1 belongs to n of a. x1 belongs to n of a. So only consider first part, ax1 is equal to x1a. So consider ax1 is equal to x1a. So multiply on both sides. Write by x1 inverse. So multiply x1 inverse. So changing the brackets, a into x1 inverse equal to x1 a into x1 inverse. So x1 into x1 inverse, already you know that a into a inverse value is e. So a into e equal to, so it can be written as, so x1 a x1 inverse. So multiply a into e value, e is the identity element, so value is a. So x1 into a x1 inverse. So multiply on both sides, left by x1 inverse. So x1 inverse. So x1 inverse into a equal to, so x1 inverse into x1 into a into x1 inverse. So x1 inverse into a equal to, already know that x1 inverse into x1 value is e, a into x1 inverse. So x1 inverse a equal to a into x1 inverse. So already you know that xa equal to ax or ax equal to xa. So that means a belongs to n of a. So x inverse a equal to a into x1 inverse. So that means x1 inverse belongs to n of a. Therefore, so this is the theorem. So next concept is center of Z. So next, center definition. Center of Z. Center of Z. So center of Z. So if Z is a group, and A belongs to Z, then X belongs to Z such that AX equal to XA or XA equal to AX for all A belongs to Z is called center Z of Z. It is denoted by Z or Z of Z. So theorem statement is, if Z is a group and A belongs to Z, so let us consider n of A equal to X belongs to Z such that AX equal to XA for all A belongs to Z. So first of all, write down the statement. If Z is a group and A belongs to Z, then n of A is a normal subgroup of Z. So Z is a group. Center of Z is a normal subgroup of Z. So theorem statement is, if G is a group and A belongs to Z, then center of Z is normal subgroup of Z. So proof. First of all, write down given points. So let Z is a group and A belongs to Z. So already you know that center of Z. So Z is equal to set of X belongs to Z such that XA equal to AX for all A belongs to Z. So consider Z is equal to X belongs to Z such that AX equal to XA for all A belongs to Z. We have to prove that center of Z or Z is a center of Z or Z. So Z is a normal subgroup of Z. We have to prove that. Z is a normal subgroup of Z. So first we have to prove that Z is a subgroup of Z. So first we have to prove that Z is a subgroup of Z. So already you know that the necessary and sufficient condition. So necessary and sufficient condition, H is a subgroup of Z if and only if AB inverse belongs to H. So B inverse belongs to H. Two conditions, AB inverse belongs to H, B inverse belongs to H. So that means H is a subgroup of Z. So another theorem, the necessary and sufficient condition. H is a subgroup of Z. So if and only if AB belongs to H, A inverse belongs to H. So the necessary and sufficient condition, H is a subgroup of Z. So this theorem can be used in, so AB inverse belongs to H, B inverse belongs to H. So finally H is a subgroup of Z. So or we have to show that AB belongs to H, A inverse belongs to H. So then H is a subgroup of Z. So using this theorem, so we have to show that AB inverse belongs to H, B inverse belongs to H. So finally H is a subgroup of Z. So first we have to prove that Z is a subgroup of Z. So first of all we have to prove AB inverse. So that means x1 x2 inverse belongs to N of A. So x1 into x2 inverse belongs to N of A. First we have to show that x2 inverse belongs to N of A. So that means let us consider, so first of all x1 x2 belongs to Z. x1 x2 belongs to Z. So subgroup center of Z, that means denoted by Z. So first we have to show that x2 inverse belongs to Z. So next we have to show that x1 into x2 inverse belongs to Z. So x2 inverse belongs to Z. First let us consider Ax1 is equal to x1A. So let x1 x2 belongs to Z. Consider Ax1 equal to x1A. So we have to show that x2 inverse or x1 inverse belongs to Z. So consider x2. So consider x2 belongs to Z. So x2 belongs to Z. So Ax2 equal to x2A. So multiply both sides right by x2 inverse. So Ax2 into x2 inverse equal to x2A into x2 inverse. So changing the brackets, A into x2 inverse equal to x2A x2 inverse. So already know that x2 into x2 inverse value is E. So A into E equal to x2 inverse into A x2 inverse. So A into E is the identity element. So A equal to, so x2 into A x2 inverse. So multiply on left side by x2 inverse. So A equal to multiply on left by, so x2 inverse into A equal to, so x2 inverse into x2 into A x2 inverse. So x2 inverse into A equal to, already you know that x2 inverse into x2 value is E into A x2 inverse. So value is x2 inverse into A equal to A x2 inverse. So that means therefore x2 inverse belongs to, so x2 inverse belongs to Z. So next we have to show that x1 into x2 inverse belongs to Z. So let next we have to show that x1 into x2 inverse belongs to Z. So let x1 x2 belongs to Z. So x1 x2 belongs to Z. Consider A x1 equal to x1A, A x2 equal to x2A. So we have to prove A x1 inverse, x1 into x2 inverse belongs to Z. So let us consider A into x1 into x2 inverse. So changing the brackets, A x1 into x2 inverse. So Ax1 can be written as x1A. So into x2 inverse. So x1 into Ax2 inverse can be written as, already you know that Ax2, so Ax2 inverse it can be written as x2 inverse A. So Ax2 inverse can be written as x2 inverse A. So changing the brackets, so it can be written as, so Ax2 inverse can be written as x2 inverse A. So changing brackets, x1 into x2 inverse into A. So therefore A into x1 into x2 inverse equal to x1 into x2 inverse into A. So Ax equal to xa. So therefore x belongs to Z. So x1 into x2 inverse belongs to Z. So therefore Z is a subgroup of Z. Subgroup of Z. So next we have to prove normal center of Z. That means Z is a normal of Z. So next we have to prove Z is a normal subgroup of Z. So let A belongs to Z, X belongs to Z. A belongs to Z, X belongs to Z. So then AX A inverse. So we have to prove AX X inverse belongs to Z. So therefore Z is a normal subgroup of Z. So AX X inverse so can be written as A into XA inverse, or so AX into A inverse. So AX can be written as XA. So XA into A inverse, so changing the brackets, X into A inverse. So A into A inverse value is E. So X, already know that X belongs to Z. So therefore AX A inverse belongs to Z. Therefore Z is a normal subgroup of Z. Z is a normal subgroup of Z. So given Z is a group and A belongs to Z. So we have to prove that center of Z. So that means Z is a normal subgroup of Z. First of all, we have to prove subgroup of Z. So next, AX A inverse belongs to Z. So that means Z is a normal subgroup of Z. So next theorem. So next theorem, if N is a normal subgroup of Z, normal subgroup of Z. So if and only if condition, so then Z by N is abelian if and only if for all A comma B belongs to or X comma Y. So X comma Y belongs to Z, XY, X inverse, Y inverse belongs to N. So if N is a normal subgroup of Z, then Z by N is abelian if and only if X comma Y belongs to Z, for all XY, X inverse, Y inverse belongs to N. So proof. So let N is a normal subgroup of Z. N is a normal subgroup of Z. So we have to prove that Z by N if and only if so XY, X inverse, Y inverse belongs to N. So consider XY, X inverse, Y inverse belongs to N. So XY, X inverse, Y inverse can be written as Yx whole inverse. So XY, X inverse can be written as XY, Yx whole inverse belongs to N. So that means XY, X inverse, Y inverse means, so already you know that Z is a group. So AB whole inverse can be written as B inverse, A inverse. So X inverse, Y inverse can be written as Yx whole inverse. So XY, already you know that since AB inverse belongs to H. So if and only if HA equal to HB. So by using this theorem, so it can be written as H means N. So N of XY is equal to N of YX. So N into XY, H into YX. So XY. So this is AB. So AB inverse belongs to H, can be written as HA HB. So NA NB. So NA NB. So already you know that H of HA HB can be written as HAB. So this is A, this is B, can be written as NX NY NY NX. Already you know that Z is a group. So Z by N, we have to prove that if and only if condition. So we have to prove that Z by N is abelian. So Z by N is abelian, already a normal subgroup of Z. So we have to prove only commutative law. So commutative law in general, AB equal to BA with respect to multiplication. So AB equal to BA. So this is commutative law. So Nx N into Ny equal to Ny into Nx. So commutative law satisfy. So let us consider xy, x inverse, y inverse belongs to N. So solve Nx into Ny equal to Ny into Nx. So if and only if condition. So xy, x inverse, y inverse belongs to N if and only if. So it can be written as yx whole inverse. Solve Nx into Ny equal to Ny into Nx. So therefore Z by N, hence Z by N is abelian if and only if x by x inverse, y inverse belongs to N.